David Verity. David.
Thank you. So I'd like to talk to you a little bit today about something which is a bit different from the normal silicon-based semiconductor industry, which is PragmatIC, and some of the things that we're doing at PragmatIC, which is a little bit different. We can't talk about PragmatIC without talking about the flexibility, and that's flexibility both in the technology and flexibility in the way that we work. So I'm going to apologize now for if I use that word too much. I don't know any better words that kind of will fit instead. So what is PragmatIC in a nutshell? So we make semiconductors. We make integrated circuits. We don't make them using silicon. We make them using alternative materials and alternative devices. The technology that we've got has all of the same kind of benefits that you get in silicon. So you get active devices like transistors, you get passive devices like resistors and capacitors, and you get multiple levels of metallization in order to connect those together. The technology itself is built onto a stack which is about 30 microns thick. So pardon me using the word again, but it's very flexible naturally. We don't need to do any thinning of the material or anything when it comes out of the fab. It just comes straight out in a format which is usable in all kinds of different form factors compared to what you're used to in rigid components from silicon. Our manufacturing lines are a little different to what you will typically find in the silicon industry. So the silicon industry relies on very big kind of gigafabs, the size of cities, huge expense, huge investment to get them up and running. Our manufacturing sites are much smaller, much more compact. They fit into an area which is about, it's less than 1,000 square meters. So the typical kind of clean room is about 20 by 30 meters. One of the big benefits that we offer over the traditional silicon industry is our technology can be turned around in the fab in a matter of days. So what we want to do as we advance the technology forwards and we improve it is be able to put parts through the line in literally a couple of days. So we can be very fast, we can be very agile with how our technology works. So in electronic systems these days, there's obviously a real push towards making things smaller, making things more lightweight, making them fit into interesting form factors. So think about, smart devices like watches, AR devices, in-ear headphones, those kind of things. You're trying to fit electronics into an ever increasingly small area and ever increasingly more interesting form factors. So rigid surface mount components on rigid PCBs don't work well for a lot of systems these days. So there's a push towards hybrid systems, like the picture in the middle here, where you have a flexible PCB with a number of rigid components on the surface of it. And what we want to do is we want to kind of push on a step further from that, and we want to offer a system where you can do at least some of the rigid surface mount components in a flexible form factor already in a flexible device, and get rid of the majority, if not all, of the surface mount components from that. I'm afraid I'm going to have to use the dreaded F word here again about the way we work. So essentially, we want to be a foundry. We don't want to be manufacturing designs that we've produced in the long run. We want to be manufacturing designs other people have given us, which will unlock a whole other area, whole other areas of places that our technology can be useful. So we want to be a pure play foundry, and that comes with all of the trappings of an ecosystem which needs to come around that foundry. So we want to have people who are designing IP, standard cells, analog IP. We want people who can offer assembly formats and different ways to package our devices or put them into or onto different things which will enable it to be used in some of these new applications, like some of the wearable ones. We also currently offer our own in-house IC design services, so that's kind of a little bit in between being basically an integrated device manufacturer and being a foundry. So we have teams who will design to the specification given to us by a customer. And we also have our own integrated devices. So we have our own range of primarily RFID devices, which we currently offer. In order to be a foundry, the most obvious thing that you need is a process design kit, which we have. It's compatible with mainstream EDA tools. So anyone who's done any design work on any silicon nodes should be able to easily access our technology. Like I already said, the idea and something we really want to offer on our technology is this kind of rapid design iteration, and give people the opportunity to quickly turn around iterations of designs in the fab and not have to worry too much about the kind of first time right methodology that you need with really advanced silicon nodes. So our process is quite a bit more simple than what you would typically see, particularly on a modern silicon node. So we don't need any of the kind of long duration processes that silicon needs. We don't need any of the high temperature processing that silicon needs. We don't need any of the high water usage steps that silicon needs. So we can make our devices much cheaper and much more sustainably than the industry is kind of used to. And that's all kind of done naturally by the fact that the stack and the devices in the stack can all be processed at these low temperatures and without these complex processing steps. So where we're at the minute is we have a production site in the northeast of England, just outside, just inside County Durham, sorry, in a place called Sedgefield, if you've heard of it. It's Tony Blair's constituency, for those of you old enough to remember him. That's where our pilot line basically is set up. So that's a 200 millimeter line. We manufacture in a wafer-based format onto a 200 millimeter glass carrier. That line with our RFID circuits is capable of producing something in the region of about 250 million devices a year. Our new line, which is going to be 300 millimeters and is going to be the UK's first 300 millimeter production facility for semiconductors, which is also located just on the outskirts of Durham, will be capable of outputting a much, much higher amount than that, so several billion of our standard RFID chips. And ultimately, our goal is to kind of scale up our manufacturing and be able to place these small, discrete manufacturing facilities, anywhere in the world where they're required. So what we really want to do is to be able to offer a service to our customers where they can choose where they want to locate their fabs, and they can place it next door to their assembly center if they want to kind of cost down their supply chain, or they can place it in an area where they can do secure manufacturing if they have a particular requirement around security. We really want to kind of play on the fact that it's very, compared to silicon, it's very cheap and very easy to install one of our facilities. So in terms of some of the kind of devices that you can do using our technology, bearing in mind it is a little bit different to silicon in terms of the way it works, you can make quite complex systems. We have a number of different achievements that we've got to over the last few years, particularly working with partners like ARM and NIMEC, where we've done something a little bit more complex than just our standard NFC chip. So our standard NFC chip on the left here is a small, roughly 3 millimeter IC. It's a few hundred NAND equivalent gates. It has a little bit of an RF front end and a little bit of memory in order to store some information. But we've also done a number of different projects where we've kind of upped the complexity somewhat of what you can do on the technology. So machine learning chips of a few thousand gates, a 6502 processor or a replica of a 6502 processor, which was all done in our flexible material. The plastic armpit project, which I believe you can read about in Nature, which was a project we worked on with ARM, where it wasn't just a digital chip. There was some analog components in there and some information coming in from a sensor, which was then being digitized and then being worked on by this chip. And the most complex chip that we've produced to date is this plastic arm project, where we've basically replicated the entire functionality of a Core M0 ARM core processor in about 18,000 gates. Now, that was done on a technology that we had available sort of a couple of years ago. The technology has iterated a little bit since, and this 60mm square die that we had for the Cortex M0, we think we can bring that down by something like a factor of between 5 and 10 these days on the technology we've got now and the technology we're going to have on the new 300mm lines. So I mentioned the RFID that we do at the moment, and these are some of the kind of use cases for our RFID products. So it enables you to kind of put some basic functionality into a whole range of objects that you maybe necessarily didn't before. So interactivity in terms of shopping is a big thing that we've been exploring. So having an NFC chip embedded in everyday materials or everyday packaging and enabling you to scan that and get a lot more information about what it is. The sustainability, so we've looked at how to use our devices, for example, in recycling plastics and having some information built into a tag in the bottle. So a plastic bottle where you can, it gives you information on what type of material and what type of plastic that's made from, and then lets you much more easily recycle it and put it down the correct line for whatever type of material it is. Authenticity and traceability are two other things we're looking at with the RFID as well. So, authenticating high-value products and traceability in things like healthcare. It's worth pointing out that these are examples of what we can do with our RFID chips, but really what we're looking to do is kind of expand out beyond that. So we're looking to do things outside of just RFID. So we're looking for other applications where perhaps silicon doesn't quite offer the right sort of cost or performance point where our technology might do something different. So we've had a lot of interest from people doing things like capacitive touch sensors or certain types of labeling or things like this, which are a little different to the standard RFID. So that's everything from me, so happy to take questions.
Thank you, David. That's grand. Thank you. And he's right, I do have a mic. If anybody has any questions, then we're open to them. Yes, I'll come to this gentleman here. What's your name?
My name is Wang.
Oh, Wang. What's your question, Wang?
I know RFID is an excellent demo case for your technology, but compared to silicon RFID, what are the key advantages?
Thank you very much, Wang.
So the form factor in the case of RFID we see as being the main one, and a little bit longer term for us, the ability to bring the cost point down. So we think because our technology is a lot cheaper than silicon, even compared to an older silicon node, we should be able to get our devices cheaper. And the fact that we can attach to an antenna which has been created on a polyimide substrate, and then that can basically be used in any kind of form factor without having to worry about the sort of, the shape of the chip or where it's sat, gives you a lot of other places that you can use it where you traditionally have to be quite careful about sort of bending the silicon chip or having it, in any kind of format other than on a flat surface. So probably those two things.
Okay, and I think we're about up to time. Will you please thank David Verity, Bobby? Thank you, David.
Thank you.
Thank you. Please welcome Kylie Wang. Kylie.
Thank you, Ian. Good afternoon, everyone. I'm Kylie Wang. I'm the business developer from Arculus Systems. Oh, this one. So, today we're going to talk about our EDA tool and what is the function, where you can use it, and when you can use it. And before that, I believe that everyone are really concerned about their anything about green or ESG. So, for our product, it's about green EDA. So, Hawaii, Greece, and Spain. I believe that everyone heard about this sad news in recent years about they had a huge damage by the global climate. So for us, it's not just only about the nature things. It has something to do with us, not just me and include everyone here for sure. So every industry try their best to think, what can they do for the Earth? And because that will be a big, huge of the economic cost. So as an EDA company, we are trying to provide our client and trying to tell the world there are many ways that we can help with the Earth. So when our clients use our EDA, there will be less RD resource, less power, less traveling, more efficient, and more sense. So let's talk about our product. So here is a little stories about our company. At a very early stage, we provide our client IP selling and IC design. And one of our clients, they are struggling with their performance because they cannot provide their performance to meet their clients' their requirements. That is the IC design house 7nm SoC projects. So they suggest by our clients, they hand over the design for us to take it a try. And they are so surprised because when we take over their designs, their performance had a great improvement. For example, for AXI bandwidth from 1.4 gigabits to 3.5 gigabits per second, that would be like 2.5 times. And about the design cycle, that would be like from 3 weeks. They use 3 weeks, but they are still trying to find the issue, by the way. But when they hand over the design for us, when we use our internal EDA tool, it increased from 3 weeks to several hours. That means that we reduce a lot of RD resource. So it also means that lower power consumptions. So our clients are really surprised, and they suggest us to make our internal use EDA tool as a product to sell. And then we try to engage more customers, and they give us a lot of good feedback. So we increase more functions. We also optimize the user experience, interface, and more make the EDA tool more and more powerful. So we are proudly to trademark our EDA tool as iProfiler. I stand for interconnection. Profiler means SoC, performance analyzer. And I believe that if you are working in a semiconductor or you are an IC designer, you're pretty familiar with this IC design floor. So this is the flow you usually take, and we simply divide it into three teams, which is from architecture design, which is for AI team, AI model team, and SoC, front-end and back-end team. So we suggest our client can have the three crucial types they can use our EDA tool. The first one is for architecture design exploration, and the second is when they're using on the RTL level, they can do the performance analysis. And they can also do the verification and debug before they hand over the design to the backend team. So we believe that when our client use our iProfiler, it's a good way to accelerate in IoT and machine learning industry during the seamless hard work and teamwork and software teamwork. And this is the complexity of the waveform. So usually, IC designer, when they finish their design, and then when they generate the file from emulator and the simulator, they usually get the VCD file. So for the designer, they usually take a lot of time to zoom in and zoom out to find the issues. So it takes a lot of time, and we can see how they enjoy their jobs. Yeah. So we are here to make their life easier. We make the report, make it into more visualized. We make the iProfiler transfer the waveform to performance intelligence. So here is an example about memory. So they have SRAM, DRAM, and flash. And you can see how much percentage they use by the pie chart. And also they can see different gate count by different address, how's the performance of the SRAM, DRAM, and flash, and so on. And of course, there are more. And iProfiler provide our clients two different types of the system diagram, which is iProfiler Cloud Edging and iProfiler On-Prem Edging. So on-cloud edging is really good for the performance to the IC designer who is a solo designer, who has a smaller design, but I want to more flexible working environment. And also we have the iProfiler On-Prem Engine, which is for those who work on site and they prefer have the group of team they want to discuss. This is a good option for them. And talking about the architecture design exploration, especially for the industry of the cloud, edge, computing, sensors, there will be on-chip and off-chip memory allocation is crucial. So for example, for the bigger on-chip memory, they have the bigger die size, and they have the really nice performance. However, for the better off-chip memory, they have the smaller die size, so they have the lower performance. Actually, there is no standard. It really depends on what kind of the application is the end customer looking for. So for example, for the consumer customer, they are probably looking for the smaller size, right? So iProfiler is a really nice EDA tool for our clients to help them with the memory allocation design exploration. Okay, so this is the SoC chip design everyone usually can see. So we encourage our clients that they can use our iProfiler and design at the same time. Maybe it takes a little time to do the design and to back and forward to modify, but we believe in the future, you may save more time at the very beginning and help their product time to market. So this is an example. So our client can put their CPU and put to the and to see the performance to the external flash, or CPU to SRAM, or CPU and to NPU. They can see how the performance if meet their requirement. And usually designer, they can set up the design rule. So there is no standard again. Just it really depends on the spec they are looking for. Okay, and the next is for IP performance explanations. When the IP vendor provide their IP, if they cannot provide the sample chip, but they can provide the RTL code, we can see they can see the report from the iProfiler to see if they meet what they claimed for before. And also, our client can do port-to-port transaction analysis, for example, to CPU to SRAM, NPU to CPU, to see how the bandwidth and the latency. And we say AI SO chip is very complicated. So it's not just like we had before. Actually, we'll have more different protocol. So for example, our client can use it for CPU, go through AXI to ABP, and so on. And for the feedback we usually have from our client is when they do the AI SoC chip design, memory access is always the bottleneck to them. So we would like to emphasize, encourage them to see they can check their memory access as well. For example, like CPU to SRAM. So we talk about what is iProfiler, how to use it, what is the feature, and now we want to share with everyone today who is the key person can use iProfiler. So we believe that AI model team, SoC front-end design team, and back-end design team, all of them can use it. Because iProfiler enables the seamless collaboration between AI model team and SoC team to generate a comprehensive cyber report for the back-end design team. So in the future, we can see if iProfiler can make the foundry house to see there will be the cyber tool for them. If they say the report is meet all the requirements, meet all the rules, and they accept the design, we believe in the future, and the end customer's product can type in market. And I believe that is everyone are looking for. So more detailed information later on. You can talk to me, and I have some flyers for you, so I can share more detailed information for you. Thank you.
Thank you, Kylie. Thank you.
Thank you.
Well, hold on. You're not going anywhere. You've got 5 minutes to see if anybody in the audience has any questions.
Okay.
Any questions out here? If not, I'm going to ask you. Oh, you can follow everybody on microip.com.
Yeah.
I want to know about who your company partner is.
All my company partners. Actually, we have ARM, and ARM and E3 in Taiwan, and we have National Jiao Tong University. Also, we have some of the partners, some of the clients, for example, Qualcomm and Motorola Solutions. Yeah.
Brilliant.
Yes.
Please welcome Dr. Wen Chen.
Thank you.
Can I give you my?
Good afternoon. My name is Wen. In the next 10 minutes or so, I hope to convince you that there is a revolution coming, at least in terms of AI hardware. But before that, I'll just quickly talk about our company. We are listed in Taiwan, as Taiwan Stock Exchange. We do customized DRAM. When you guys think about DRAM, you think of Samsung, Hynix. That's not what we do. They do standard DRAM. We take the same technology, we customize it to make it better for the particular applications that we target. So that, hence the application in AI. So the title is 3D IC innovation. So here, I will start by describing a problem that everybody knows about. Over the last 30, 50 years, computing has been increasing by whatever magnitude you can read from the chart. But the key here is memory is not. Memory is much, much slower. And this hasn't really been a big problem for CPU computing. CPU somehow has managed to live with a slower memory for all this time. But it is a huge problem for AI, and I'll show you why. And the way we measure AI performance or machine learning performance is by this formula. It's deceivingly simple. The way we measure that is by counting how many flops or how many operations per second. And the way we calculate that is by doing two parts. One is how many operations can you do given a fixed amount of data or given a number of bytes. And the second term is how many bytes can you bring in per second. And the second term here, how many bytes can you bring in per second, is memory bandwidth. Therefore, memory bandwidth is actually proportional to AI performance, to the first order. And there are other limitations. Without other limitations, memory bandwidth is proportional to AI performance. In other words, if other things keep improving, you will eventually be limited by memory bandwidth, and that is actually what's happening today. And what's interesting here is that memory bandwidth is rooted in hardware. And this chart is supposed to represent a PCB, a long distance, and few wires, and that's what limits the traditional memory bandwidth. And this is 2.5D. That's how all the AI hardware is made today, by putting HBM next to an SoC. And here we have 1,024 wires that are spaced over a few millimeters. And here, I would argue that there is a severe limitation that this architecture cannot overcome. The reason is these chips being side by side, the amount of space that you have for these wires, what's known as beachfront, is limited by the size of the chips. Therefore, the number of wires is limited to some degree. And you may be able to go to 2,000, but I can't see that you can go to 10,000. And the speed by which you run these wires is also limited. Therefore, we believe the only way to break through this bandwidth bottleneck is by making these chips in 3D fashion, stacking DRAM directly on top of logic. I know what you're going to ask next. Can we really do it? We have actually built this. We started this in 2018 or so. Our first project went into production in 2021. And the way we do it is like this. We take a DRAM wafer. We trademark it as VHM. Our DRAM technology customized for this purpose is called VHM. We take an SoC wafer. We stack them face to face. Once you stack them, the cross-section looks like one wafer. logic on top, DRAM on the bottom, and there are some connections in between. They are practically like one wafer. But because like they are like one wafer, the communication between DRAM and logic is so fast and so the distance is so short, and that's how we can achieve the bandwidth. And this technology has been in production for a couple of years. With this chip, we're taking this chip as an example. For the particular application that they have, which is actually Ethereum mining, compared to the leading edge GPUs, we're able to achieve about 10 times the performance at about a third of the power. And that's the power of this technology. So what we're saying here is that given this chart, with the 3D IC technology that we have, we will see memory bandwidth shoot up, get closer to logic. And that is the revolution that I was talking about. And I can see this means a huge change to semiconductor industry in many ways, not just semiconductor industry, but also in terms of policy. So let me just kind of list a few. I'm sure there are a lot more. In terms of memory, if you think of memory companies, like I said, you think of the standard DRAM companies. We believe if we go in this route, standard DRAM will become custom memory. And that's a completely different business model. And design will change from logic-centric design to memory-centric. And technology will change from scaling-centric to advanced packaging-centric, and so on. So I won't say too much about that stuff, but I will leave a few minutes for questions. Thank you.
Thank you very much. Are there any questions I should ask? There's a chap at the... Oh, it's you. Hello. Hello. David, hi. What's your question?
Me again. So this is very memory-centric, the kind of way you're combining chips together here, but are you looking also at combining, multiple different digital chips or digital chips with kind of, as digital accelerators alongside more analog-centric circuits and those kind of things?
Absolutely. I think this is not our focus. The technology of 3D stacking applies to logic as well. And there are some use cases where we find logic stacking helpful. For example, hardware emulation, you need a lot of gates. You need a lot of FPGA, very high volume, very high scale FPGA. You might want to stack logic. But for machine learning kind of thing, mainly we're talking about logic memory bandwidth.
Any other questions? Yes, I'll come to this chap down here. Hazim, what's your question?
I'm curious about, so you've talked about the impact that this has had on Ethereum mining, but the main focus on the talk has been how this can accelerate, for example, the memory bandwidth bottlenecks for artificial intelligence.
Yes.
Have we seen any real impact there, and are we looking to demonstrate any real impact there in the future?
Yeah, that's an excellent question. I forgot to mention that the reason we chose Ethereum mining as the first application case is that Ethereum mining follows exactly the same formula. Performance is proportional to the bandwidth. That's why we chose that algorithm to demonstrate the technology. And that's also the reason, that's the same, the similar reason applies to why we didn't choose AI. Because for AI, the architecture of SoC is a bit more complicated. They need to do more customization to make it happen. And that's coming, that's following this. It will come soon. You will see it.
Okay, any more questions? Wang, you make a very strong case for why 3D is the future. Why, just a presumptuous question, why aren't other people jumping on the bandwagon? Why aren't other people doing it?
You'll be surprised how many people are doing it.
Okay.
You just don't hear about them. Yeah, so the reason people don't talk about it is because the ecosystem is not quite there yet. If you think of 2.5D, it's been going on for 10 years. It has a huge install base. And this is new. And from our point of view, we offer IP. We want to go out there and pump our chest and try to sell IP. For our customers, they want to keep quiet. And that's why.
Okay. Any other questions? Just chap at the back. I shall totter over. There you are. What's your name?
Ken again.
Oh, Ken, sorry.
So actually,
There's
fans
a strong light, so I'll come a little bit closer.
Yeah, thanks a lot for your presentation. So just one simple question. So we are now also kind of a heterogeneous structure. So could your 3D stacking technology comply with the heterogeneous structure? Is we are having chiplet and etc. So could your 3D stacking comply with? Yeah.
So heterogeneous integration simply means you put wafers of different variety together. And 3D stacking is one form of heterogeneous integration. 3D stacking clearly can do heterogeneous. You can put pretty much any kind of wafers together. So these are pretty much the same thing, just a different way of looking at it.
Okay. Any other questions? I should come to this. Making me run around and it is warm. Neil,
yes. You mentioned the big DRAM companies.
Yes.
Are they too big to innovate in this way? Or I mean, I'm assuming they're the ones with the technology to actually manufacture it.
So this is another very, very interesting question. So there are two things that prevent them from being the first, at least. They might be the last or they might be second. Number one is their business model is standard DRAM based. The reason they are so big and they are so powerful is because they can pump out 100,000 wafers a month of the same device from the same fab. Right? So this is by nature customized. This violates their manufacturing model, business model. Right? That's number one. Number two is their business is so good. Right? Why bother with something that's way out there? You know, it takes a lot of work. It's not really their organizational culture to do something new. And that applies to, right, that applies to a lot of industries. You know, old companies don't do new things. Yeah.
So what is the manufacturing challenge for you? Sorry, what's the manufacturing challenge for you then in terms of who's going to manufacture these chips on it? What's the volume like in terms of who's going to pick this up?
Yeah, so we actually have enabled a bunch of manufacturers to partner with us. This is one of the jobs that we have to do to create the ecosystem, including manufacturers who can do this. We have a number of them, including PSMC earlier this morning, and TSMC as well. And some others. Actually, the challenge here is not so much in manufacturing. The manufacturing technology is relatively simple. The challenge here is, number one, in how to customize the memory and make this memory work in this setting. This is different, completely different. There's a lot of technical details, but it's very different from standard DRAM design and manufacturing. And the other challenge, which is probably, it gets back to your question, why AI isn't here yet. All the AI designs have to learn how to use this memory technology. So if you think of this 2.5D, data is coming from the edge. Now data is raining down on you. It's a completely different architecture. The data is raining down on you at a much faster rate. They need to learn how to deal with that. So there are companies who are trying to figure that out, and the companies that do will lead the revolution, I hope, along with us. Yeah.
Brilliant. Yeah. Thank you very much. Any other questions? In that case, I could give you one last chance, Ken, but no. In that case, thank you very much indeed to Chen, everybody.
Thank you.
Thank you.